Quantum computer, something that recently a lot of people speak about it. Of course, you guys have already familiar with these words. Technology that is capable doing something that ordinary computers cannot do. But do you guys actually know how quantum computer works? Some words we often hear from this technology like superposition, entanglement, qubit. Well, something that sounds great and seems like complicated, so different from how classic computer works nowadays. So in this video, we're gonna discuss how does this technology get started, from the very beginning of this concept appears.
The word quantum computer is a little bit misleading because it sounds like a computer. And when people think of computer, they think of a phone or a laptop. The truth is the phone and the laptop and even a very powerful supercomputer all operate according to the same fundamental rules. And a quantum computer is fundamentally different.
So let's get started. You guys might know him. Yes, Richard Feynman, a scientist who lived around 1918 to 1988, which became the first person who began to realize the limitation of classic computer.
On the other hand, I think I can safely say that nobody understands quantum mechanics.
Even though he didn't propose quantum computers explicitly, but he many times stated the limitation classic computer to simulate quantum physics by saying, nature isn't classical. Damn it. And if you want to make a simulation of nature, you better make it quantum mechanical. Then what? Well, the idea didn't just stop there, because at the end of 1960s, a Soviet mathematician and physicist named Yuri Manin came out with his writing entitled Вычислимой и невычислимой, or Computable and Uncountable.
It is extremely natural ones. They are not artificial ones. You calculate some partially recursive function, and if you try to calculate it at a point where it is not defined, but you will never know it. You calculate and calculate and calculate, you never get an answer, but probably if you wait 1,000 years more, you will get it. So there are infinities of very intrinsic kind in computability theory. And of course, the scheme of calculation can be also imagined as a graph, say, graph of states of Turing machine or whatever. There are many different ways to do it. So I thought probably because graphs are there and graphs are here and infinities are there and infinities are here, so why not to try to do renormalization in computer science?
Important to note that it was not a book about quantum computer, but one of the first masterpieces which explicitly realized that classical computational models perhaps not enough to describe the nature process. Alexander Holevo. Perhaps some of you don't know him. He is a mathematician which became popular when he came out with his theory, Holevo theorem, become critical thing in quantum concept. His theory proves that the amount of classical information that can be extracted from quantum system is limited, no matter how advanced the measurement.
As my talk started from understanding quantum limits. So practical optical quantum channels, they suffer from limitations. So these capacity results, they just give you absolute bounds which cannot be superseded by any efforts.
The information that can be obtained through any best measurement is less than or equal to the Holevo quantity. This concept, later known as Holevo bounds. Well, some of you guys might ask why is this important? So, before him, to be precise around 1960s to 1970s, physicists have understood superposition and entanglement. But the question was how many classic information that actually we can take from quantum system. It becomes such a paradox because as we know that qubit has continued amplitude, so why don't we send unlimited classic information by one qubit? But actually was wrong. We cannot do that because the nature allow itself. Nature have limited it.
So the question that the Holevo bound addresses is how large can this accessible information be, right? What is the maximum accessible information for a given ensemble of quantum states?
And just so you know guys, that at that time, quantum computers were still something I would say that people knew to simulate things related to physics only. That means people didn't know that quantum computer can actually become universal computation model as well as modern computer nowadays. So the question rises up, does quantum machine capable to run common algorithm like classic computer? And surprisingly, it answered by David Deutsch in 1985 through his paper entitled Quantum Theory, the Church-Turing Principle, and the Universal Quantum Computer. For you who doesn't know him, he is a theoretical physicist and a professor at University of Oxford. He is also one of the physicists who support many words interpretation.
Applies to the multiverse interpretation of quantum mechanics, as in, is the particle that doesn't collapse, or the collapse of the wave function that doesn't take place, is that now real in separate universes? And can you explain sort of simply to a layman what the reality of that looks like?
Yes, well, I'm always slightly provoked when someone calls that an interpretation of quantum mechanics, because no one says that about the theory of evolution or other theories in physics. We say we have a theory. We're well aware that it might not be perfect, but it is our claim as to what reality is like. It's our best claim as to what reality is like. In quantum mechanics, things have gone wrong thanks to that bad philosophy that I spoke of earlier. And the fact is that there are experiments where one can show that individual quantum particles are strongly affected by something that is never seen. This is quite familiar in physics. Even Newton postulated invisible fields of force, not fields, invisible forces. That operated on the planets, even though one can never see a force, and never perceive a force.
Well, what it is first, it is the idea that the physical world that we see around us, the room, the stars, galaxies, and so on, is just one tiny sliver of the whole of reality. And the whole of reality includes many such objects, many of the kinds of objects that we have traditionally thought of as the universe. And so it's sometimes called the many universes theory. I actually prefer I prefer to call it the multiverse theory, because it contains a lot more than just those things that we used to call universes. It contains other structure as well. So the whole thing as a whole, reality as a whole, is the multiverse.
Important to note that in his paper, he actually doesn't tell about qubit, but about the meaning of computation if universe is quantum. David Deutsch emphasized that quantum computers are not special tools, but rather a complete model of computation. This idea will later drive the massive development of quantum computers. Everything seemed fine until Shor's algorithm appeared. Around 1994, Shor's algorithm appeared and shocked the world, especially the world of internet security or cryptography. As we know that internet security relies on RSA, DB-Hellman, and DSA, all of which rely on the difficulty of factoring large numbers and the discrete logarithm problem. Initially, this problem was practically impossible for classical computers to solve in a reasonable time.
Well, it's actually very difficult to compute phi if we don't know what p and q are. So computing phi of n can be done very quickly with this expression. But this expression relies on the fact that we know what the primes are.
It should not computationally feasible to find a. So this is the discrete logarithm problem. So you have the generator. When I give you a, you can add this generator to itself or multiply in this notation to itself a many times and obtain the result. But when I give you the output and ask you which power of g it is, it should be hard for you to find. Okay, this is how we define the discrete logarithm problem.
But after 1994, it was no longer. Peter Shor, a mathematician at AT&T Bell Labs, with his breakthrough discovered that factorization problems can be reduced to period finding problem, and period finding can be solved efficiently by quantum computers. This is the gap that Shor's algorithm can exploit by reducing factorization to period finding, performing a quantum period transform, and extracting the period efficiently in practice. If a large enough quantum computer is available, it can easily break all cryptography based on factorization and discrete logarithms such as RSA. Well, this makes the entire internet security seem like it is under a countdown.
A normal computer, even a very powerful one, is very slow. Like, to find the factors of this number, it took 2,000 years of computer processor time. Now, it's not yet proven that we won't eventually find a fast way to break encryption just with normal computers, but it's certain that anybody with a large working quantum computer today would pose an immediate privacy and security threat to the whole internet. And that's due to something called Shor's algorithm.
There are some public key crypto systems that the discrete log problem is the key to breaking it. If you could solve the discrete log problem, you could break the crypto systems. So a similar thing holds for factoring. If you can factor large numbers rapidly, you can break the RSA crypto system. But discrete log problem, you break the Diffie-Hellman crypto system, which is not as common, but which is still a very important problem.
The threat doesn't stop there, because after Shor's algorithm, Grover's algorithm emerged and became the second breakthrough after Shor's, but with a very different character. If Shor's algorithm broke public key cryptography, then Grover touched all symmetric cryptography and hashes through brute force acceleration. Previously, people thought that quantum computers were only dangerous for RSA and discrete logs, and not for IES, hashes like SHA and passwords. The assumption at the time was that brute force was an absolute limit, but Grover's algorithm broke all that. Grover's algorithm was introduced by Love Grover, a computer scientist at Bell Labs. He showed that quantum computers could search in unstructured space faster using a quadratic speedups, O times n squared. Unlike classical computers that try each possibility one by one, quantum computers create a superposition of all possibilities, mark the correct solution, use amplitude amplification, enlarge the possible solution, and repeat it up to n squared times.
I'll tell you what turns out is the algorithm effectively becomes half as strong because of a thing called Grover's algorithm. Grover's weakens symmetric algorithms by half.
Unlike Shor's algorithm that can break cryptographic keys, Grover's algorithm cannot. Grover's algorithm only reduces the security by half. For example, IES 128 would be equivalent to 64-bit security. AES 256 will be equivalent to 128-bit security, and so on.
Now the good news is, if we want to go ahead and overcome the cracking capabilities of the quantum computer, all I have to do is just make the key twice as long.
This is the reason why modern standards have to increase key lengths.
In Bitcoin's case, it can reduce the effective strength of its SHA-256 hashing from 256 bits to about 128 bits. That sounds dramatic, but 128-bit security is still considered extremely strong. It's the same level used in modern online banking and secure messaging. And if the day ever came when that felt too low, the fix would be simple: upgrade to a longer hash.